Okay, so in class on Friday, we started on the 3.9 rates and related rates worksheet. We did examples 1. We talked about a little bit of a process to this, and we did example 2. Now I'm going to continue on with example 3. So this is example 3 from the 3.9 related rates handout. In this example, it says air is pumped into a ball at 4.5 feet cubed per minute. Find the rate of change of the radius when the radius is 2 feet. Right, so like I said, we always want to start with some sort of a process. I'm going to write what I know and make sure I'm aware of what I'm trying to find. So based on the first sentence, I'm told air is pumped into a ball at 4.5 feet cubed per minute. Right, so this is something that I know, and if you think about air being pumped into the ball, it's going to expand, meaning that the volume of the ball is going to be changing. And if you think about the units given, it says feet cubed on top per minute. So I know that cubic feet is going to represent volume. So this tells me that the change in my volume, so dV, with respect to the change in time, dt, is given as 4.5 feet cubed per minute. Right? The next piece that I need to draw out is what I want to find. So I took care of my first sentence with the no part. Now I need to think about what I want. And this says find the rate of change of the radius when the radius is 2 feet. So if I put that in Leibniz notation, the rate of change of the radius would be dr. This is with respect to t, so I have dt. And I want this when r is equal to 2 feet. Okay, if we think about this further, with the dr dt when r equals 2 feet, thinking about the radius and what's going on, you should recognize that this radius is changing. So as you pump air into the ball is getting larger and larger and larger, which means the radius is getting larger and larger. Therefore, the radius is not a constant, so you can't just plug it into whatever equation we make from the get-go. We have to do that at the very end after we take the derivative. Okay, so now from the process that I gave you on Friday, we need to create an equation. So create an equation that relates our two rates here. So we know our rates involve V and R. So V and R, because those are the things that I want and the things that I know. Okay, well, this one, if you don't remember, the volume of a sphere, a ball is a sphere. So a volume of a sphere is 4/3 pi r cubed. So nicely enough, this works great because we have the V that we want, we have the R that we want. Therefore, we know as soon as we take the derivative, we get the two rates that we're trying to relate with this equation. Right, so at this point, now that I know I have a good equation to work with, I can take the derivative of both sides, and I need to do so with respect to t. So when I do this, the derivative of v with respect to t is dv dt. Okay, on the right-hand side of the equation, 4/3 pi is just a constant, so I don't have to worry about that. But r cubed, I need to use the power rule on, and I also need to recognize that since the r doesn't match with the t I'm taking the derivative with respect to, I'm going to have to use implicit differentiation. So dropping the 3 down by the power rule, I'd get 3/3, which divides out to 1, so I'm just left with a 4 here. And I'm rewriting my pi, and then I'll have an r squared. So this is technically the derivative of the outside of r. I still need the derivative of the inside, so the derivative of the inside is dr dt. Okay, at this point I've completely taken my derivatives, so now that I've done that, I can fill in the information that I have. So fill in given info. Right, when I do this, I'm given that dv dt is equal to 4.5 feet cubed per minute equals, then I'm going to rewrite the 4 pi, and I know that I want dr dt when r equals 2 feet, so I fill in my 2 feet for r. Okay, and then I don't know dr dt, so I'm just going to have to rewrite that. All right, simplifying this just a little bit, I see this is the same as 4.5 feet cubed per minute. I'm going to divide that by 4 pi times 2 feet squared. because dr dt is here and I need to divide it by this to get rid of it, so dr dt is isolated. And then I also noticed that 2 squared is 4 times 4 is a 16. Rewrite the pi, and then that also gives me a feet squared. Okay, and now I've completely isolated dr dt, so I'm just going to simplify this a little bit, make sure my answer makes sense, and make sure that my units make sense. Okay, so for my answer with my constants, I see that I have a 4.5 over 16 pi. This is positive. It makes sense because if we're pushing air into a ball, we know that the radius is going to get larger, so it makes sense that the change in radius would be positive. Okay, and now to take care of our units, I see I have a feet squared in the denominator and a feet squared in the numerator. Sorry, feet cubed in the numerator. So feet cubed over feet squared is just going to be feet. And then of course I have the minutes in the denominator here. Okay, so units-wise, this also makes sense because the radius would just be in feet and time is in minutes. So our answer seems pretty logical. Oops. Okay, I'm going to go ahead and clear this board. If you need to look at it, you can of course rewind the video, so it shouldn't be too big of a deal. And then I want to get started on number 4. All right, so number 4 on our 3.9 notes. Number 4 says, an 8-foot ladder is leaning against a wall. The top of the ladder is sliding down the wall at a rate of 2 feet per second. How fast is the bottom of the ladder moving along the ground at the point in time when the bottom of the ladder is 4 feet from the wall? Okay, so on this part, okay, I had a brief interruption there. All right, I think I read the whole first question, but either way, we have to chip away through the whole thing and get every piece that we need out of it, or sorry, everything we know and everything that we want. So first, I'm just going to start by re-going through the question and writing every component that I know or what I'm given. So I know that I have an 8-foot ladder. Okay, and if you think about this, a ladder is going to be constant, right? You're not going to change the length of the ladder. It's going to stay the same every single time. So I know that this is definitely going to be constant. So I definitely have this 8-foot ladder. That's a constant. Right, now I want to think about what this looks like a little bit too. So it says an 8-foot ladder leaning against a wall. So I'm just going to say that I have a wall right here. And then this 8-foot ladder right here is leaning against it. So I know this length right here is a constant of 8 because that ladder length is never going to change. Okay, so that takes care of our first sentence. The second sentence says the top of the ladder is sliding down the wall at a rate of 2 feet per second. Okay, so now in order to write this, I need to give the wall some sort of a name. So I'm just going to call the wall y. And I'm given that I have dy dt. Right, so if you think about it, as this ladder slides down, this length y right here is going to change. So I'm giving really y the name to this length here. So that gives me that dy dt equals, and since it's moving down, I'm going to do a negative 2 feet per second. Okay, so that takes care of my second sentence. The third sentence asks, how fast is the bottom of the ladder moving along the ground at the point in time when the bottom of the ladder is 4 feet from the wall? Okay, so here's the bottom of the ladder. Here's the wall. We're thinking about the movement of this ladder. So if you think about it, if my ladder is here, as it slides, it's going to extend out this way, which means this side length right here is going to change. So since it's changing, I'm going to make sure it's a variable and call it x. And this tells me that I want, how fast this side length, so this horizontal length x is changing. So dx dt when, and then it says the ladder is 4 feet from the wall. So when x is equal to 4 feet. Okay, so now I've basically read through, gathered all information I can from each section or each sentence in this question. The next thing that I need to do, is to find an equation that relates x, because I want x right here, y, and my ladder length. Okay, well, if you think about your prereq skills, I have this nice little drawing in a triangle that's a right triangle, and in your head right now you should be thinking, oh yeah, the Pythagorean theorem is what is going to relate those three things. So by the Pythagorean theorem, I know that, I'll even write that out, by the Pythagorean theorem, we know that x squared plus y squared is going to equal to 8 squared. And I should be thinking, this is great, I'm so happy because as soon as I take the derivatives, I get the dx dt, or I will get the dx dt that I want, and I will have the dy dt that I know in there. So let's go ahead and take our derivative. If we're looking at the x squared part, we're taking this derivative with respect to t, not with respect to x, so I know I need implicit differentiation. The derivative of the outside will be 2x, the derivative of the inside, so the x will be dx dt. Okay, same idea for the y squared. The derivative of the outside is 2y, the derivative of the inside is dy dt. Right? And then the derivative of 8 squared is just 0 because 8 squared is a constant. It's not changing. That derivative is definitely 0. All right, so at this point, I've got my equation, I've taken my derivative, I see that I have all the pieces that I know in there and that I want in there, so I'm going to fill in my given info. Oops. Given info. And see where we're at. Okay, so I know I have 2 times. I wanted this one, x was 4 feet, so I fill in a 4 feet for that. I don't know what dx dt is, I'm trying to find it, so I'm just going to rewrite it. And then I have plus, let's see, 2, okay, this is a problem, at least right now. We don't know what y is, so I'm just going to have to write that. I do know that dy dt was given as negative 2 feet per, I'm going to scroll up here real quick, second. Okay, equals 0. All right, so now if we look at what we should see like, oh, wait a second here. I have a little bit of a problem. If you have an equation with 2 unknowns, so dx dt and y being our unknowns, then you're not going to be able to solve for what you want, which is dx dt. So basically we need to get y, and that's because we can't have 2 unknowns. Okay, so you might be running out of space on your paper. Usually when I do this, I just solve for y right underneath this triangle. So from what I have before, I know that x squared plus y squared is 8 squared. Well, x squared, or sorry, the x that I want is 4 feet, so I can fill in a 4 squared. And then I have plus y squared equals 8 squared is 64. So really I have y squared equals 4 squared is 16, and 64 minus 16 is 48. So I should see, or I can see, that the y is equal to the root of 48. And then of course on this you only keep the positive solution from square rooting, and that's because it wouldn't make any sense to have a negative length of a triangle or a negative length of a wall. So I'm going to keep this as is, and I'm going to use my y and plug it back in. Okay, so now I'm going to plug in my y. When I do this, I have 2 times 4 over here is just 8, so I have an 8 feet dx dt plus 2 times my y, which is root 48, and I know that my units with that will be feet as well because it's a side length. And then that's times my negative 2. Oopsie, whoa. Sorry. Hopefully you can still see that. Do this. Try to erase some of this. It's finicky. Okay. All right. Okay, so we have the negative 2 feet per second on that part. All right, so essentially from here, I'm pretty excited because I've done quite a bit of work, but I see that the only thing I have left is the dx dt, so as soon as I solve for that, I'm going to be done. All right, so the first thing I'm going to do is rewrite this. I'm going to subtract all of this stuff over to the right and simplify it a bit. So I know that -2 times 2 is actually a -4, which means I add this to the other side. So I get a 4 times root 48. And then I see that, let's see, I have a feet times a feet, so that's going to be in feet squared per second. All right, now to isolate dx dt, I'll divide both sides by 8. So I get dx dt equals 4 over 8 is really 1/2. So I have a root 48 over 2. And then I have, with my units, a feet squared over seconds over feet, because I divided a feet over right here. Okay, so at this point, if you go through your square root part, you can, if you want to, simplify that, or you can write it as a decimal. I don't really care, honestly, so I'm just going to leave that as is. So I have dx dt equals root 48 over 2. And now I just need to adjust my units. I see I have a feet squared over feet. That ends up just being feet per second. Right, now let's think, does this make sense? Well, first, I know that x is a ground length, so it makes sense that that would be in terms of feet. And I see that root 48 over 2 is positive. And if you go back to your image and really think about what's going on, if this ladder here is sliding out this way, it would make sense that this length x would be increasing. So it is pretty logical, and it makes sense that we are getting a positive answer there. So my answer is logical. Steps look pretty good, which means I can feel pretty comfortable with this calculation.